Yeah, I think you can
Okay,
start
good
the.
afternoon. Yeah, we are just going to start because everyone almost come and we are waiting for our HOD sir, Saha sir. But I think we can start now. Okay, so good afternoon, all the members here and our external ma'am, Anindita ma'am. So with your
Good afternoon,
permission,
sir.
then we are going to start the defense of Prabhat Das.
Yeah, definitely, sir. We can start it.
Yeah, so Prabhat, now you may proceed.
Okay, sir. Ma'am, I hope this screen is visible.
Yes, it is.
Okay.
So,
So,
good
good
evening
evening
to
to everyone.
Excuse
My
me,
name is
Prabhat. There is an echo happening, so maybe multiple microphones are turned on.
Okay. Okay. So yes, good evening to everyone. My name is Prabhat Das. So for the past couple of years, I've been pursuing my research on the topic development of an optimal approach towards IoT data analysis using clustering techniques under the guidance of Dr. Dibya Bora sir and Professor Dr. Sajal Saha sir. So right now I'm in a stage to defend my work. So what we have done for the past couple of years. So let's move ahead with the presentation. Uh, Moving with the content slide, as you can see, these are my brief contents that we are going to present and discuss today. Starting from the introduction, motivation and problem context, followed by research gaps and problem statements, then the objectives that we have laid down, then the methodology and the experimental setup that we have carried to fulfill those objectives, then the real-time batch framework that we have modified, and the results and discussion, followed by the contribution, conclusion, feature work, references, and appendix. So let's get started with the introduction. Now, towards the left of my screen, you can see towards the right of the screen, you can see that there is a Coke vending machine. And we have the year 1982. What exactly this Coca-Cola vending machine is doing over here? So this demarks the inception of the famous technology, which we know as Internet of Things as on date. So what exactly this is? This was the combination of ingenuity and laziness, where the students of Carnegie Mellon University, in order to overcome their laziness, developed a machine which could not only give the status of the number of Coca-Cola bottles and the status about the temperature sitting right on the top floor of the university campus, whereas this machine was placed in the third floor. So this was where, because of the laziness, they could come up with a solution where just sitting in a remote location, they could understand the status of the products that were available. So this was what which was later known as the Internet of Things. But in the year 1982, this was the inception based on which this entire technology got started. Now, moving on to today, this is what exactly Internet of Things is all about. Now, you can see starting from the domain of medical to agriculture to smart cities, everywhere we have this Internet of Things. Now, what exactly this Internet of Things is all about? It's all about connecting those devices with the internet. Now, based on this uh, entire technology, when we did some of the surveys, we came to know that uh, year on year, the number of devices that are getting connected to each other is increasing significantly. Now, in this graph, you can see that in the year 2015, we had a total number of around 3.8 billion devices, which got spiked to around 21.5 billion just within a span of 10 years. Now, year on year, we had a growth of around 11.8%. All the statistics were represented from the famous portal, that's IoT Analytics. Now, we all know that as the number of devices increases, right, as the number of IoT devices increases, there is always uh, an increase in IoT data. So if devices are increasing, then definitely these devices are communicating with each other, and as a result, data is also getting increased. Now the question is, what to do with this data that is increasing day by day? So we came up with an idea of, let us try to analyze this data so that we can come to an informed decisions right after analyzing this data. Now, while going through this, we came to know that in a result, in a nutshell, we can divide the analysis into these 7 major categories, roughly, starting from the descriptive, like what happened, then diagnostics, how it happened, whatever it happened, and when it will happen next. That's the predictive, prescriptive, how it can be prevented, followed by the real-time analytics, edge, and cognitive, like adding the intelligence to this entire analytics. Now, based on this 7 major categories, we thought of let's move ahead and let's do some survey what exactly work people have done in order to solve these problems. Now, presenting few brief literature surveys which we have already gone through during our entire research work, starting with this paper which was primarily based on predictive analytics, where this paper was completely conceptual, where they surveyed all those existing IoT analytical solutions and how exactly ML and DL was used to overcome or used to solve those problems related to those predictive analytics. No new algorithm was proposed, and moreover, there was no real-time data streams that exactly happened. Now, if we move ahead to the next paper, it was again a survey level paper. Again, no new algorithm proposed, and no real-time data streaming was done. Again, it was a kind of survey paper. Moreover, it was an predictive analytics kind of paper. Now, moving ahead to the next paper, again, this was once more a survey paper. Again, they discuss about the importance of real-time and IoT data solutions, mostly discussing about the clustering, how clustering could solve those kind of problems. But again, the research gap remains the same. There were no techniques which could handle the low latency data, and rigorous evaluation of IoT data streams were very much required. Now, if we move ahead, this was something where they discussed about diagnostics and detective analytics, majorly based on rule-based techniques. Again, lack of intelligence and no adaptive learning. And if we move ahead, this paper that we had was all about descriptive and predictive. It was good because they mainly focused on routing and energy efficiency with reference to IoT devices. But the issue that came up with this entire statement was that, again, no real-time analytics and no streaming data was considered for this particular survey. And eventually, we found a gap of where we could incorporate unsupervised clustering algorithms for performing real-time analysis. Now, moving ahead to this was related to the diagnostics and descriptive analytics, where we could see that they performed analysis with reference to IoT data, but again, yes, the entire data set was completely an offline data set. Basically, online data or the streaming data was still missing in this entire picture. This was something which had the flavor of real-time analytics, but the issue with this paper was that it had a concept of window-based protocol. Basically, a timestamp-based protocol. Let's say after a period of 10 minutes or 5 minutes, they captured the data and they performed the analysis. Again, no hardcore real-time. So with this said, with this brief literature review, what I wanted to explain is, here we found some gaps, like scope of improvements in this entire scenario of IoT data, where the real-time analytics can be incorporated to solve the modern day problems. So the gaps that we found is scalability gap, adaptability gap, latency gap, security gap, interpretability gap, and integration gap, and the last one, evaluation gap. Basically, a standard benchmark data set could be used to evaluate all those existing technique. Latency could be improved, security could be improved, and obviously, we needed a solution which was real-time in true sense. With this said, we came up with our problem statement. The problem statement: to design and implement an efficient, scalable, and dynamic clustering technique capable of handling large structured and unstructured IoT data in real time with minimum time complexity and automatic cluster detection, enabling informed decision making. So with this problem statement, we thought of laying down our objectives. So what are the objectives we laid down? As in all, total, we had 4 objectives, where the first objective says to develop an improved clustering algorithm with less time complexity, which could also handle and determine the number of clusters more efficiently and accurately with reference to large volume of IoT datasets, obviously. The second one, to analyze these clusters using the improved clustering algorithm to find the hidden patterns for both structured and unstructured data, to form clusters of similar IoT devices to reduce the latency in IoT data transmission, and last one, to detect vulnerabilities in these clusters of similar IoT devices formed with the proposed clustering based approach. Now, based on all those four methodology which we laid down, there was this need how exactly we could proceed with those methodology and how could we solve those problems. So here comes our methodology. So basically this entire methodology is divided into 6 phases, which I'm going to discuss as of now. So the starting or the first phase that we had is discussing or understanding the baseline algorithms, all the existing algorithms which we already had. So we can see here is a hierarchical representation of all those clustering algorithms which we already have, starting from the message passing to graph based, distribution based, centroid based, fuzzy based, overlapping based, hierarchical based, and density based. Now, while performing a literature survey with the existing data and simulating it into a real-time format, we came to know that out of all these algorithms, the algorithm which got our eye into it and which had a better performance was Birch. Because Birch was that algorithm which not only had a least amount of execution time, but also the number of clusters that were generated from this particular algorithm was very much efficient, as well as they had minimum or no overlapping as such. In the phase 2, we thought of planning the architecture, how exactly we can do the setup, because it involved some hardware equipments, edge computing devices that needed to be deployed across a specific geofenced location, which could be monitored again. So we came up with this architecture where we thought of deploying 6 ESP32 with DHT11 for capturing the temperature and humidity across a specific location, which I'm going to show. And all those devices were responsible to send the data to a localhost server, which had the network of class A IP address. And again, they propagated the entire data to MongoDB. From there, propagated to Oracle Cloud Computing Virtual Machine Instance. And at the same time, it had a parallel propagation with ThingSpeak Cloud just for visualization purpose. But the main analytical purpose could be handled by the MongoDB database that we have deployed. And lastly, we had a web interface through which we can track all those activities, see the heartbeat of this IoT sensors, and also we can perform the real-time analytics. Now, this is the snapshot of the configuration of the machine that we had. It had a RAM of 256 GB, and obviously it had 64 cores. And yes, as you can see, the gigahertz of the processor is 2.6 Intel Xeon processor. And in the next phase, what we thought of is we had 2 objectives, if you remember, that is to handle the structured data as well as to handle the unstructured data. For the unstructured data, we came up with the solution of deploying Raspberry Pi along with camera sensor across various locations. Again, the same methodology, it will be propagated to the localhost server where the MongoDB is installed. And from there, we will be performing a real-time analytics in a data processing layer, obviously the virtual machine instance where the entire computation is going to happen. And finally, we are going to display the data into the web interface. Now, to show how exactly the entire scenario looked like, this is how it looked like. Towards the right, if you can see, we have the Raspberry Pi devices along with the camera sensors installed in various locations, their IP addresses and the MAC addresses. As you can see, it already has the class A IP address, and towards the left, all the ESP32 devices along with the geotag photos and the various locations where they were deployed for a specific period of time to send the real-time data. Now, as in all, total, we had 2 physical clusters communicating with each other, obviously, through the center server, the cluster of capturing the structured data and the cluster of capturing the unstructured data. This is what the geographical location looks like and the various locations where we have deployed the devices across the campus. Yes. Now, moving ahead to the phase 4, where we thought of pre-processing the data and move ahead with the experimental setup and evaluate the matrices based on some standard mechanisms such as Silhout and Davies-Baldwin. Along with that, also we calculated the execution time and the memory usage to understand the overall performance of this entire algorithm that we are going to proceed with. And in the phase 5, if you see, this is what exactly the pictorial representation of a step-by-step process for the vulnerability detection looks like, where we deployed the various devices across the university. We move ahead with a 4-phase mechanism, where initially we launched a DDoS attack under this entire framework. Then we followed the DDoS attack with the deauthentication attack, where right after DDoS attack, when the devices got choked and they got stopped, we launched deauthentication packets such that those devices which were connected to the network can get deauthenticated. And right after deauthentication, this was the time where we launched our evil twin attack. Where in the evil twin attack, we mimicked the same SSID such that when the devices wanted to reconnect, it could reconnect to our spoofed SSID. And lastly, just to get the packets from those ESP32 devices, we launched the last attack, that's the MITM, which was the last nail of the coffin, where right after launching the MITM attack, what we did is we got the entire data packets which were getting propagated through this network. Now, this is what exactly the sitemap of the web application looked like. Like the standard mechanism where we had the login dashboard followed by the dashboard to show the device status and the real-time analytics, where we had the option to perform the clustering with k-means, Birch, dbscan, and the modified real-time Birch, which we came up with. And towards the right-hand side, you can see the flowchart of how exactly the entire mechanism worked. And the phase 6, in order to validate this entire scenario, we thought of using some benchmark data sets. We used some famous benchmark data sets which are globally renowned, such as the RT IoT 2022 Air IoT, CIC's IoT IDAD 2024, which is a vulnerability based data set. And what we did is we compared this with some existing streaming mechanisms like the clue stream, cluster stream, and the DB stream. And we came to a conclusion of how exactly this entire algorithm which we developed, or the framework, is performing against those existing mechanisms. Now, if you remember, I already said that the existing algorithm Birch came out to be one of the good performing algorithm. Now, what was the reason behind the good performance was that it had an amazing speed. That means the time complexity was less. Next, the clusters that got generated was very good enough. There were nominal overlapping. And we thought of incorporating it into a real-time scenario because that was the missing part of this existing algorithm. And lastly, which is most important thing, that it could handle large data sets very efficiently. Now, if we try to see the mathematical model of this existing Birch algorithm is that Birch is completely based on CF trees. That's the cluster feature trees, which requires the number of data points, linear sum, the squared sum, the calculation of centroid, and the radius. The equation for the calculation of linear sum, squared sum, the centroid, radius, and the distance is already given, provided that right after calculating the radius, there is a condition whether to merge the data point or keep the data point into a cluster, or whether to create a separate cluster is completely based on a static value. That's the threshold value. In all those frameworks or the libraries that we use by sklearn, right, the issue with those libraries are that they have a static threshold, and because this is what exactly the Birch algorithm defined, that they need to have a static threshold of around 0.5, 0.6, something like that. So the thing is that why it was required and why the static value of threshold was defined. The reason was because Birch was never designed to handle real-time data. And we saw the capability in Birch, and we thought of tweaking it such that we can use it or extend it further for handling the real-time scenarios as well. Now, this is where the change happens. Like the modified real-time Birch, that is the algorithm or the model that we have proposed. here, in order to come up with a solution, we introduce an hybrid mechanism, a mechanism which is based on OS level and kernel level and hardware level. The second mechanism, which included the tweaking or adaptive and improving the adaptability of the threshold value. So if you see, what we did is, as soon as the data point got ingested, we divided the data point into multiple threads. So as a total of 10 threads were created, and in those 10 threads, those data points were equivalently divided. Followed by which we perform the CF tree calculation in a global scale, where all those values which were calculated in these individual threads gets calculated in a global scale, and as in all total, we get a component addition of all those CF trees, which is represented in the equation that has been highlighted. But here, if you see, this particular condition is same, that we are still using the structural threshold which is already being inherited in the existing Birch configuration. So what is the change that we bought? We bought a change of 95% quartile range, because this is something which enhanced the entire performance of the Birch and converted Birch to a real-time algorithm, where what we did is we introduced a 95% quartile distance mechanism, where all those centroid distances which were calculated for each CF trees, out of this entire array, we took the threshold value of all those data points which were more than or less than the 95% of the quartile range. So basically, if I have 10 data points of distance, so out of those 10 data points, all those values which are less than the 95% value, those particular values were considered, and that particular value which is considered for the 95 percentile will be calculated as the threshold. This was our approach. So, and this is an adaptive approach because this happens in an iterative fashion. Along with that, which existing Birch didn't do, and what we did is we also implemented the squared of sum errors such that the neo elbow locator can be calculated, and we can frequently evaluate the number of clusters, whether the clusters that is getting generated is efficient or not. This is the architecture that we came up with. As soon as the data comes, it has to be divided into multiple threads in the form of chunks for parallel calculations. Moving ahead with that, it will be sent to the Birch clustering framework. That is our proposed equation that we can see. And from there, all those computation will be directly sent back to the server, which is responsible for displaying the data into the web through AJAX. That's asynchronous JavaScript and XML, such that in a real-time manner, these data points or these graphs can be updated frequently. Moving ahead with the results and discussions. As I've already said that we move ahead with the existing clustering algorithms, and we found that the Birch was one of the best performing algorithms, where we can see that these are the results where the execution times are already presented, and we highlighted values for Birches already mentioned, where we can see that it had a very good execution time across all those data points, starting from 40,000 scale to 1 lakh scale, like starting from 2.83 to 3.8, 3.4, 3.68, 3.94, 4.26, and 4.47. And this is how exactly the clusters look like. As you can see, the clusters are well separated, no overlapping as such, and it had a very good performance overall. This was the result of the existing Birch. So we thought of utilizing this and coming up with our own solution, where we can see that here itself, this particular graph represents the execution time of our real-time Birch, where we can see the real-time Birch when compared with Birch, dbScan, and K-means had an overall low execution time. And as you can see in this particular slide, here what we are doing is we are presenting the execution time as well as the execution time of real-time Birch in comparison with K-means, dbScan, and the existing Birch. Here also, the overall execution time or the average execution time was found to be very less, and the average execution time in comparison to the real-time Birch and K-means and dbScan, as you can see, is comparatively less than the others. This is the overall memory consumption That was the memory consumption in terms of megabytes. Here also we can see that the overall memory consumption of the modified birch is very less. That's approximately 632.6 megabytes. And if we compare the same with birch, dbscan and kbeans, we had a memory size of around 55,422 megabytes, which is very huge. Theoretically, it's possible, but practically we had to stop the algorithm again and again because we don't have, physically we don't have so much of RAM. Now, if you compare this with the state of the art techniques, then we can see the modified algorithm was compared along with those benchmark data sets, which I've already said, the real-time IoT 2020, Air IoT, CIC. All those data sets were produced by renowned institutes such as Canadian Institute of Cybersecurity and IIIT Hyderabad and National Institute of Engineering, Mysore. Those are already benchmark data sets and available in IoT data port, and all those data are being cited through very good journals. Now, throughout all those data points or the data sets that we have gathered, we can see that we took the existing state-of-the-art streaming clustering techniques such as the clue string, where we can see these are the performance and the Delvi's Baldwin index, which is basically used to check the quality of the clusters in the between the inter clusters. We have majorly we use Silhouette and the Davis Baldwin index, where the Silhouette is used for intra cluster and DBI is mostly used for inter cluster quality checking. Here also we found that the modified birch came out to be good in terms of both Silhouette and DBI score. In a nutshell, just to present all this result, we have a comprehensive graph which represents the entire scenario. This is it, where we can see that the overall Silhouette and DBI for birch was better in comparison with other algorithms. Now next, what we did is we also tried to figure out the anomalies using this particular data points, where we can see that here the clustering algorithm was performing very good in order to identify the anomalies. Because of the projector screen, these data points are not visible. But yes, the markings that we have done, here the green point and there is a yellow point over there. Those were the anomalies where you can see the temperature reading is shown as 253 degrees Celsius, which is practically impossible and was shown as an anomaly. Now, one of the objectives that we had was to calculate or to find the hidden patterns for both structured and unstructured data. For structured data, the algorithm was performing very good and we could find the anomalies very easily and the outliers very easily. Now, moving ahead to unstructured data, specifically the images that we have taken for consideration. This was the basic flow where along with the Raspberry Pi and the camera sensor, we extracted the images using the VGG16. Now, there is a reason why we used VGG16. Although there are better models such as ResNet 50 or ResNet 101, even VGG17, 18 are also available. The reason behind this was because VGG16 was very simple model and very good if we compare it with the time. Because we wanted to make the time very less, the execution time. We wanted to reduce the execution time. That's why we have used the VGG16 model to extract the features. And the features extracted from those images are as follows, as you can see in this correlation heat map. Specifically, the average intensity, standard intensity, entropy, the mean RGB values, and the standard RGB values. And from this was the results that we got from the features that we have extracted. And as we can see that from the features that we have extracted, the modified birch or the real-time birch that we developed was struggling a little bit to cluster the features that we have extracted. It was performing good. It was doing the real time. It was doing the clustering in the real time. But as we can see, there are a few overlappings, which we have already highlighted. And if we compare the same with structured data, this is the performance that we got. If we compare it with structured and unstructured data, where structured data, in case of structured data, we got an average Silhouette of around 0.87. And for unstructured, we got a score of around 0.81. Execution time is obviously high because yes, there is a layer where we had to extract the features from the images. And yes, overall the features or the clustering that was done was mostly based on the color, the entropy, and the mean RGB values. Now, if we move ahead with the vulnerability detection for the data which was getting generated from this IoT devices, first what we did is we used the tool Wireshark at the phase 1, and in order to automate the center process, we used Scapy from Python, which is an amazing library which does the same with reference to Wireshark to extract all those packets, information of the packets. Now, here is a correlation heat map of all the information that we extracted from the packets that were getting transferred from the IoT devices to the endpoint or the server. Now, in this graph, if you can see, we are representing the values in such a way that towards the left-hand side, we can see that the packet rate which is getting flowed in a normal time, that is, which is under non-DDoS attack scenario, is around 20 to 30 packets in every second. But as soon as we launch DDoS attack, the number of packets gets increased, and here we have around 11,000, 12,000. Even it reaches, there was a certain point it reached 1 lakh packets also, right? And if we see towards the left-hand side, here the packets which was shown that was getting transferred in a non-DAuth scenario was a nominal, it was flown in a nominal way. Because here we had a maximum of around 200, 300. But the moment we launched deauthentication packets, the packet rate suddenly abruptly dropped to 0. Now, taking these points as a consideration, we thought of clustering the data and thought of labeling the data based on two major scenarios. Whether the packets that we are capturing are malicious or non-malicious. Now here, right after clustering, right, we thought of using those labeled data for classification. Now, the reason why we used classification is because we wanted to classify whether the attacks or the packets that we are getting is a malicious packet or a non-malicious packet, and out of which XGBoost was the one which performed better in comparison with all those existing models. Now you can see that the accuracy, the precision, recall, and the F1 score all had a good performance. This is the confusion matrix of the same. The packet rates, the packets, the dashboard that was used for capturing the insights, and the result that we got with reference to the real-time clustering, which was later used as a labeled data set for the classification models. Now, this was all with reference to the IoT domain, like whatever we had. Now, with reference to non-IoT domain, we wanted to explore, or we want to take this entire real-time burst further, such that we could see how exactly the real-time burst performed with reference to non-IoT domains. So we came up with two solutions. Number one, the first solution was to use this in an education-based platform using the Grok hardware accelerator, and the second one was for resume scanning. Now here you see is the comprehensive view of the architecture that we deployed for the testmate application that we deployed, that was completely for an educational platform, where what we did is we used Grok's API to give the prompt, respond to that particular prompt. But if we know, if somebody have already used Grok's API, then we know that Grok, it's not the Twitter's Grok, it's GROQ, the hardware accelerator Grok. What they do is they give very limited amount of token size, and the number of prompts that we can supply is very less. So what we wanted is we wanted to build a pipeline such that as soon as a particular API gets exhausted, we can shift to a next API. For example, if I'm using Olama's API, I could shift to GPT's API. From GPT to, again, if I want, I can shift to BART or something like that. That means this entire pipeline should happen dynamically based on user preferences. So for this purpose, we thought of using this real-time clustering approach. Now, with clustering, if we wanted to see the average response time from those APIs, we found that the average response time without clustering for every prompt that the user was giving us was around 27.4 seconds, then 21.1, 22.1 for generating the question, because again this was this entire tool was designed for educational platform. Then the average token size that was getting exhausted without clustering was around 300. Then if we see concurrent number of users which could use that particular platform was around 110, and the number of error recovery score was around 5.5. But the moment we did clustering, right, we could get an improved scores, with where we can see that there is an improvement of around 23.6% in average response time, 40.3% in average question generation time, 40.6, 31.8, and improvement of around 2.3, that is 2.3 score with reference to the error recovery. And the second application which we had, this was the application which I showed was the first application, that's the testmate, which we built just to check whether we can use clustering to optimize the prompts with reference to API calls. And the second application which we built was with reference to application tracking system and application filtering system. While doing a quick literature survey, a quick literature review, we got to know that all existing companies, all existing tools, whatever we have, is completely based on ATS mode. ATS mode is we supply our resumes, they do a quick scanning based on NLP obviously, and they come up with a score that this is the tentative score for this particular resume. And based on those scores, they keep a threshold. Okay, if those resumes are beyond this threshold, we are going to select this candidate or shortlist this candidate, and rest we are not going to select this candidates. Basically, hardbound kind of thing. So we thought of coming up with a two-layer mechanism where we had ATS along with AFS, application tracking system along with application filtering system. So this is what exactly the proposed model looked like. So we got some original CV data, then we took it to generate a synthetic data with GAN, and we generate an enormous amount of data, which was around 2 to 3 lakh records, which is equivalent to 2 to 3 lakh candidates for CVs. And we took the data to our hybrid platform where we can see that again we have the data processing layer followed by the real-time clustering, where we were clustering this data points, basically those features that we took, and again sending it as a labeled data to our supervised models so that those classification can be done, presenting it into a web dashboard, and finally so that we can come to a conclusion based on which we had a plan of selecting those CVs based on 5 classifications or 5 labels, such as good scores, excellent scores, average CVs, below average, and the last one is that's the poor category. Here we gradually increased the number of CVs to see whether the algorithm was able to cluster the CVs properly or not. So here towards the left and right, you can see there are clusters which are represented. Towards the left shows the initial phase where we started with 12,500 rows and we kept on incrementing it with 12,500. That means 12,500 plus 12,500. So the next one that you see is of 25,000. Again 25,000 plus 12,500. We got 37,500 rows. Again, we still have 2 clusters. Again, we incremented it to 50,000. 62,500, 75,000 rows. This is where we see the changes, where we can see this algorithm is able to classify those CVs because now we have variations in CVs. Now, all those were treated as a label data for our supervised model. Here we were surprised to see that random forest classifier was performing very good, and this is the ROC curve where you can see the area under the curve. Average area under the curve was around 0.63, which is decent enough to be treated as a useful model. And the overall contribution of this entire framework was to come up with a solution of a real-time solution for IoT data, a framework for real-time anomaly and vulnerability detection, a framework for both structured and unstructured data, a framework for non-streaming data. This is none other than the Purge. So coming to the conclusion, so yes, now we have a solution where we can perform the analysis on a real-time basis, and moreover, the second thing is that it can not only be used for IoT platforms but also for non-IoT platforms, and upon that we could also handle or specify or carefully observe or capture the patterns from those data which we're collecting in a real-time fashion, with obviously being adaptive threshold being the major part of this entire technique. But yes, every work comes with merit and demerit. Here, some of the scopes where we could find that this particular technique can be improved was like the plan that we have to use this for smart agriculture, where even in my thesis I've presented that if we can use this clustering algorithms for efficient drone-based spraying on paddy fields, because every location or every area of a particular paddy field or a particular farming field doesn't require spraying. So if we can spray based on targeting locations, that only this particular zone will be sprayed with reference to pesticides or insecticides, whatever we have, or any fertilizer, such that the spraying can be done in an optimized way. So this is some of the work which we are thinking. And obviously, since we have captured or since we have done the entire work based on Euclidean distance, so we have a future scope where we could use noisy environments, because yes, IoT data if we consider is highly susceptible to noise. So if we can handle those noise, and also with terms to bossy data condition, such as, let's say, within a second we got a bombard of, let's say, 2 lakh data points. Now how to handle those 2 lakh data points? Obviously we'll be requiring some message queuing techniques and integration with deep learning techniques and auto encoder based techniques. Again, this is time consuming. The reason behind this, because for real time, that is just the data point comes, you put it into a cluster, it's challenging for that. So we have kept it as a future work. And the last but not the least is to enhance the privacy with reference to edge computing devices based on federated learning. This is some of the references of the study, very brief one. And this is the publication status. As in our total, we have 7 publications, out of which we have 1 Scopus and 1 SCI journal, Q1 journal, that had an impact factor of 2.5. And the third journal is under review. Hopefully within a month or so, we'll be getting the result. And the rest of the papers are conference papers. All of them are Scopus index papers, out of which paper number 5 is the paper where we got the best paper award, where like we presented the work of a vulnerability detection. This is the graphical abstract of the entire work, what exactly we have done, like a very comprehensive way. Like the data comes and goes through the real-time batch pipeline, the clustering happens, anomaly gets detected, and this is where we make our informed decision. And this is the entire dashboard that you can see, where the real-time pipelines are happening and the clustering are being done, where you can see right after, towards the top left corner, if you see, the moment the anomaly gets detected, we get a skewed cluster. Like there is a stack of the vertical stack of clusters, and towards the extreme corner we'll be seeing the outliers, and towards the bottom corner, if you see, represents the heartbeat, and towards the right bottom corner, if you see, is the MongoDB's interface, where the data is getting ingested frequently. So that's pretty much it. Thank you so much.
All the members present here, if you have any query, like to know more on something, then please go ahead.
Yes.
Good afternoon, madam.
Good afternoon, sir. Yes. Firstly, Mr. Prabhat, first of all, let me offer you my sincere congratulations.
Yes.
Completing a PhD thesis is no small achievement. It requires years of disciplined work, intellectual resilience, and the courage to venture into unsolved problems. You have produced a substantial piece of research with multiple published papers and a real working system. This is genuinely impressive. Well done. However, I have got a few questions to ask you, only with a genuine desire to understand your thinking.
Okay.
So firstly, my first question is that in your work, you have said that the conventional clustering algorithms are unsuitable for IoT due to static parameters and an inability to handle concept drift. But streaming clustering algorithms like ClueStream, DenseStream, and Clusttree were explicitly designed for this. Could you share what specific novel improvement your real-time BERT algorithm offers over these methods, apart from being an adaptation of BERT?
Okay, so apart from the adaptation technique, yes. Apart from the adaptation technique, we could see the improvement was with reference to execution time and the memory consumption. Because the challenges with reference to edge computing devices are that we have very limited amount of resources. So in that case, it's very challenging for edge devices to use those particular streaming techniques.
Parallel computing also going on.
Yes.
Okay. So coming to your limitations of limited resources and all, you have said that you want to extend your work for agriculture, right? For smart agriculture purpose. So there you have got limited resources for computation as well as extreme low bandwidth intermittent connectivity.
Yes.
So in such cases, how do you plan to modify your algorithm for handling these kind of challenges in smart agriculture?
Yes. We have a plan. If we obviously it is completely dependent on the funding because we are thinking to apply for projects. So what the plan is all about, a typical amount of wattage that has been consumed by an ESP32 is around it's around 10 to 20 milliwatts. Which is very nominal if you compare it with standard modern electronics that we have. And the most powerful one, if you go with Jetson Nano, what we have seen is around 25 to 30 watt. So I'm comparing milliwatt with watt. And if we strike down a little bit, we have devices which also consumes that's completely the ARM-based AMP series AMP Cortex chipsets, which consumes wattage around nanowatt, so which is very less. If we can utilize those devices along with solar power, obviously because yes, for agriculture purposes, we cannot pull the wiring till the paddy field. It is a challenging process, and obviously we'll be requiring constant electric supply. So we are thinking to use solar power, where there will be solar plate installed. Right below it, we'll be having like a rod. Beneath which we'll be having a photovoltaic cell, which the solar panel will be charging, inside which we are thinking to deploy our edge devices. And yes, the challenge here, this is still not this is just the part. The major challenge happens or starts with the internet. Because connectivity becomes the challenge. So here we are thinking of using LoRa sensors. So LoRa sensors, what we have done is when doing a survey, we have found that it has a range of thousands of kilometers. So if we can propagate the data via the LoRa sensors, I think we can achieve something. So it's still undeterministic.
Okay. Another question, like you have specified that your algorithm, that real-time BERT, in this case, in your thesis, you have mentioned that for the experimental setup, you re-estimate the optimal number of clusters, that is K star, every 10 minutes.
Yes.
So in a high velocity IoT stream, like for example, when we are going for a financial trading or autonomous vehicle sensor fusion, is this 10-minute recalibration truly a real-time system?
Yes, this 10-minute, yes, I agree to your point. 10 minutes recalibration is a little bit high. The reason why we have kept it as 10 minutes is because the method or the SC score that we used to calculate the knee locator, we found that it was computationally very expensive. So that's why we kept it 10 minutes. But yes, we are thinking to improve it because yes, your question is absolutely valid. If this can be improved with reference to the actual data, like for example for stock market, where there is a frequent changes happening. So in that case, this particular evaluation technique will not work because 10-minute time is a huge time where we can see a dip within a fraction of seconds or fraction of minutes.
Yes, moreover, your framework uses a powerful cloud virtual machine like 256 GB RAM. So, how would your contributions translate to a true edge or fog computing scenario where a Raspberry Pi or a gateway device might have only 1 to 2 GB of RAM or a
Yes.
low power CPU? In that case, will this be suitable?
Yes,
Yes,
ma'am.
ma'am.
That's
That's
what
what
if you
if you
see,
see,
we
we
did
did
an
an analysis
analysis on
on
two
two
specific
specific
devices
devices
because
because
yes,
yes,
well, for
for
every
every
edge
edge
computing
computing
devices,
devices
we'll
will
be
be
requiring
requiring
some
some
amount of
amount of
RAM
RAM
to
to
work on
work
with the
on with the
data
data
because
because
ultimately the
ultimately the
processing is
processing is
going to
going to
work on
work
the
on the
RAM
RAM
itself.
itself.
So
So
for
for
this,
this,
we
we
have
have
utilized
utilized
Pi,
Pi,
which takes
which
around
takes around
5
5
wattage
wattage
of power
power
supply,
supply,
and
and
Jetson
Jetson
Nano,
Nano,
which
which
takes
takes
around
around
25
25
watts
watts
of
of
power
power
supply.
supply.
Both of
Both
them
of them
were suitable
were
enough,
suitable
but
enough,
yes,
but yes,
Pi
Pi
3
3
was
was
facing a
facing a
challenge,
challenge,
but with
but with
reference to
reference to
version Pi
version Pi
4 and
4
Pi
and Pi
5,
5,
the
the
entire
entire
system was
system was
working
working
very
very
efficiently.
efficiently.
Pi
Pi
3
3
was
was
challenging
challenging
because
because
with
with
1 GB
1 GB
RAM,
RAM,
because
because
OS
OS
also
also
takes
takes
some
some
sort of
sort of
memory,
memory,
but
but
instead of
instead of
using the
using the
Raspberry Pi
Raspberry Pi
GUI
GUI
version, if
version,
we
if we
install
install
just the
just the
CLI
CLI
version,
version,
which
which
doesn't
doesn't
have the
have the
GUI
GUI
and
and
consumes
consumes
the
the
basic
basic
Linux,
Linux,
just the
just the
terminal
terminal
itself
itself
without
without
GUI.
GUI.
In
In
that
that
case,
case,
Pi
Pi
3 will
3 will
also
also
work
work
because
because
it
it
will, in
will,
the
in the
back end,
back
it
end,
will
it will
consume
consume
very
very
low
low
amount of
amount
RAM.
of RAM.
Okay. Also, you have shown your result with respect to execution time and memory, but did you measure any other operational metrics that is critical for IoT, like, for example, energy consumption per data point on the edge device or the network bandwidth usage for transmitting clustering features to the cloud?
Yes,
Yes,
yes.
yes.
We
We
didn't
didn't
like,
man,
can you
can you
please
please
repeat?
repeat?
There were
There
2
were 2
points.
points.
One was
One was
regarding the
regarding the
bandwidth, and the
bandwidth, and the
second one.
second one.
I'm saying that you have reported with respect to execution time and memory, but did you look into like energy consumption per data point on the edge device or network bandwidth usage for transmitting clustering features to the cloud? Did you look into those points, how exactly your algorithm is behaving with these parameters?
For yes,
For
for energy
for
consumption,
energy consumption,
like
like
there is
there is
like what we did is we
what we did
did
is
a
we
rough
did a rough
estimation
estimation
because we
because
were
we
very
were
much
very much
there was a
there was a
challenge
challenge
to
to
deploy those
deploy those
devices
devices
across
across
all
all those
various
various
locations.
locations.
So we
So
did
we
a
did
quick
a quick
survey of like how
of
much
like how
wattage
much
that needs to
wattage
be
that needs
supplied
to
and
be
how much
supplied
power
and how much
is
power is
consumed
being consumed
while
while
transmitting those data
transmitting those
from
data
one
from
point to
one
the
point to the
another.
another.
And with
And with
reference to the
reference to the
bandwidth or the
bandwidth or the
latency,
latency,
we
we
could
could
see
see
that
that
minimum
a
of
minimum of
one
one
capital M
capital M
small b
small
PS,
b
that's
PS, that's
megabits per second,
megabits per second,
or let's
or
say
let's say
2
2
megabits per
megabits per
second
second
is
is
also
also
enough
enough
to
to
transmit the
transmit the
data.
data.
But if we
But if we
have
have
a
a
speed of
speed of
around
around
like
like
10 to
10 to
like
like
around
around
10 to
10 to
20
20
megabits per
megabits per
second
second
is
is
good
good
or
or
decent
decent
enough
enough
under the
under the
circumstances
circumstances
and
and
under
under
the
the
area where
area
we
where we
did
did
this analysis.
analysis.
But
But
yes,
yes,
the
the
moment
moment
we
we
expand expand our
expand our
network,
network,
because this
because
was
this was
completely
completely
done
done
under
under
controlled
controlled
experimental
experimental
setup.
setup.
So if
So
we
if we
move
move
ahead
ahead
with
with
a real-time
real-time
deployment
deployment
where
where
we don't have control over
over
this
this
entire
entire
environment,
environment,
I
I
think
think
that will
that
be
will be
challenging.
challenging.
Okay. One more question. Like you use the custom collected data from the ESP32 or the Raspberry Pi devices and used proprietary Grok API. Now,
Yes.
how do you think an independent researcher could fully replicate your core results? I mean, is this custom data set that you have developed, is it archived publicly or
Yes,
Yes.
it's
It's
okay,
available in my
available in my
GitHub
GitHub
profile.
profile.
okay.
Like
Like
the
the
paper
paper
that I
that
have
I have
shown over
over
here,
here,
Mm-hmm.
uh, this
this
one,
one,
Mm-hmm.
the
the
CI
CI
paper,
paper,
Hmm.
like
like
the
the
where we
where
are
we are
proposing
proposing
our
our
birch
birch
algorithm.
algorithm.
There
There
itself in the
itself in the
conclusion,
conclusion,
we
we
have
have
kept
kept
the
the
accessibility of
accessibility of
data,
data,
where
where
anyone
anyone who is
who
who
wants to
wants to
access the
access the
data
data
can
can
access it
access it
through
through
my
my
GitHub
GitHub
profile.
profile.
Okay, okay. Now, my last question from my side. Actually, when I was reading your thesis, I came across somewhere that you have mentioned your similarity report shows a similarity index of 1%. Now, which is exceptionally low. How did you achieve this? I mean, we are struggling every day to with the similarity index and all. So, how did you manage to get this 1% similarity index?
To be
To be
honest, I
honest, I
didn't do
didn't do
anything
anything
like
like
any
any
juggling or
jugglery or
something like
something like
that.
that.
The
The
only
only
thing
thing
was
was
before
before
moving
moving
ahead
ahead
with
with
Buildbit, I
Buildbit, I
was
was
constantly repeatedly
repeatedly
there
there
were
were
multiple
multiple
iterations
iterations
using
using
authenticate and
authenticate and
turn it in.
turn it in.
So
So Eventually, in identity and turnitin itself, we got a stability index of around 5% or something, which was comparatively low compared to individual bit.
Last time it was 9%. Then
9%.
it is 5%, and ultimately it is 1%.
Okay, okay. Good work, Prabhat. Thank you for like sharing your work with us, work with me rather. Actually, I have really enjoyed your work, and it's a nice thing, the nice work that you have done over here. Okay, so congratulations. Shall I call you like Dr. Prabhat Dash now?
On you, man. You.
Anyway.
Thank you so much, ma'am.
Yeah. Thank you so much. Thank you so much for inviting me as well. Thank you, Professor Sajal sir. It was really nice to be a part of this presentation.
Okay, thank you, ma'am.
Thank you, ma'am.
Now, I request all the members here, if you have any query, you should ask.
I have one question actually.
Yes.
When you see the data,
Yes.
it is a server level. If there will be position of various device,
Yes.
same data, same time, then how much is loss of data, how you can calculate that?
On that,
was the question.
yes. This was a big challenge actually we faced. So what we did is in the server, we implemented Kafka. So we have Kafka clusters. What they are doing is they are parallelly, there's a broker, which is what it is doing is it is capturing all this data, and it is sending those data to the like main computation server in the form of message queues. And we have a publisher and subscriber model based on which we are handling this loss. Because throughout all those industries like Rapido, Uber, Blinkit, any real-time application where we order our food or order our booking cab service, because there are parallelly lot of longer data that are happening parallelly. They also internally use Kafka. So only because of Kafka, it was able to we were able to handle it.
But you are not having your own algorithm.
No, for that, because Kafka was already the best industry standard and the best. So we used it.
And the question, when you tell me how much percentage is loss? It's not loss. If you use the Kafka, then again the data.
Yes. Again, it will be propagated. Yes.
So, at real time, you have not studied the loss, amount of loss, like percent data you will be anyway using.
Like we didn't face any loss because we were able to see all the data with reference to timestamp. But yes, if you can mathematically calculate it, I will definitely look into it.
Yes. In all cases, you are compatible with that this amount of RAM, this amount of memory time is required. Instead of doing that, we are not calculating the time complexity and space complexity.
We calculated
rather than specifying with this high 60 GB RAM,
Yes.
this hypercore
Yes.
because basic time engineering.
Yes.
So your computational complexity actually give the performance of your
Yes.
So why you are not doing that?
We did it, and it's already present in my thesis and in my paper. The time complexity that we have is of order of n. Yes, order of n. Yes. In both the cases. Yeah, it's order of n.
Another thing is that what Sajal was asking, there is Kappa model is basically rely on the TML, the time division multiplication.
Yes.
So your all the edge devices like sensor you are using,
Yes.
your sensor, moisture, temperature, as well as you are taking some
Images, yes.
So the images for what? I said that temperature and that will give you the raw data. Image will give you some RGB values.
Yes.
So what type of image you are going to feed it and what classification you do with it?
Yes. So basically, we wanted to detect objects. Basically, again, object detection. If we use or if we compare it with standard GLO models, they are basically pre-trained models where already the images are being labeled and you can easily identify the objects. But what we wanted is we wanted to do the labeling on real-time basis.
That's okay. But in your eyewitness camera is used for what?
Camera was used. Okay, fine, sir. For surveillance.
For surveillance.
After the time series data, after a certain period of time, it is taking the data only, whether any person is going over there or not. So that the algorithm can be implemented over there.
So that also sometimes that's also sometimes not only classification, it's required detection also.
Detection also.
Yes, fine. So in the KV algorithm, we are taking some Euclidean distance
Yes,
and basically minimizing using L2 norms, that
Yes,
is
yes,
MSc
yes.
algorithm.
Yes.
That's why your error function is always going to be converged or something. It is a
Yes.
standard model. But the new things we have included in that cases. Okay. If your particularly if the dimension are very high, then
That's why, like, this was the reason why we didn't opt for K-means. We went with Birch.
yeah.
The working mechanism of Birch is
I
different.
just add one point. In the Birch, we have increased the data size from 10,000 to 1 lakh. You go to the table, you'll find out that after 40,000 K-means stopped. Means that entire 256 GB server also get caught crashed. Because it is diverging. The data is not converging over there.
So that's why before that the PCA or something kind can.
Yeah, principal component analysis could be used to reduce the dimension. But again, if we reduce the dimension, the true sense of the data will be lost. So that's why.
At least on what is the I mean, did you calculate what type of real time data are coming? What is their I think spread of the data, that is your sigma values is how much is there? Mean and sigma values are.
Yes, the distance was calculated. The distance that we calculated, that's completely variational. We didn't got a static value because it's completely variational.
Over the time it's a
It's a Gaussian value. It's completely variational.
It's a Gaussian number of Gaussian, some linear, some Gaussian.
Yes.
So if that PCA can be work properly. So why you are telling that PCA is not work, will not work? Did you did it or not?
No, like for the principal component analysis, the reason why we didn't do is because we wanted the data to keep it as it is. Again, if we can
because of that, saying that if whatever you are proposing, that require more number of iterations. So before the iteration, if you make it, your number of iterations will be less, and your definitely computation complexity will be an order of it. That will be same because it's nothing but addition because what you are question addition. But real time it will give you the more accuracy. That's why I'm asking.
That's why we introduced a multi-threading concept over here.
Multi-threading is also a Gaussian sum.
Gaussian sum, yes.
So that's why you take with the logarithm log n.
Yes.
But it's whatever it may be, you are falling under your NP complete proof.
Yes.
So
Now it's
doing on cycle loop. So why not coming out before of that loop so that it will be more faster? Why you are not thinking like that? That's my point.
Okay, definitely I will think from that point of view as well. Because initially what we wanted is we wanted to perform some sort of calculation just to come to the ultimate conclusion.
So another thing is your different IoT devices. Suppose ESP32 actually what I might remember that it can support 3 volt and 5 volt.
Yes, both 3.3 and 5.
3.3 and 5 volt. And its range, what is the inbuilt antenna range? That is near about 2.4
gigahertz nowadays, 5 gigahertz.
That is for the Wi-Fi range.
Wi-Fi
you are using IoT cases.
Yes.
So normally we are going to use some GSM SIM or something like that.
No, sir. Nowadays, ESP32 also supports 4G LTE, 5G LTE. Yes.
GSM SIM is a GSM, GSM 1.2 signal lag.
Yes.
That is 4G, 5G is a communication protocol.
Yes.
So that's a 2.4 gigahertz you are using. So why you are not thinking about the more powerful sensors? That is their inbuilt sensor can go up. But I saw like that it can go maximum 10 meters, not more than that.
So 2.4 is for Wi-Fi surround, but not for like what we have ESP32 along with GSM sensors. 4G.
First of all, because the GSM range is 900 megahertz to 1800 megahertz. And that becomes in the license band category. Such cases, I have to take the 5 GSM same and connect it and cost will be much higher. So why should I go for this one? My main purpose is to take the temperature and the job is done. Why should I go for this costly affair over there?
He's talking about to not only the local network, if we go to the global network like that, which is
This work is not
global
if you see the whatever the application area has been done, it is only within the local version. Nothing.
No, one thing I'd like to add, we can use LoRa sensors, sir.
LoRa
LoRa has
one
1 kilometer range.
So
Yes.
But again, in the LoRa also, the LoRa, whatever bandwidth earlier it was provided, right now it has come out from the ISM band. LoRa,
what is the frequency range?
even 1.5, 1.8, 2.4, 2.8,
Yeah, that's the thing. 2.4 is available. That's what I'm checking.
No, right now the LoRa bandwidth is already taken out from the ISM band because LoRa is never
That's the thing I'm talking about. If you are talking about the ESP32 or something, which is
See, there are several protocols there. We can use any one of them. Our job not is to check with different kinds of protocols. That is not the PhD work. My PhD work is focused and totally focused on a particular vertical unit. You are doing this one. There are lots of scope. You may have different kinds of ideas that can be implemented. That can be another PhD. It is not about this one.
No. Actually, the IoT part I am asking about, the most of the one is going for the ML and DL techniques we are talking about. The particularly IoT part, I am improving the IoT part. Whatever constituent will be the IoT part. How to data will be there. First of all, you are getting the time series data. Number one. Number one, would you consider the frequency series data?
No.
That's not considered. So that's why in the frequency interference, for the same frequency, 2.4, whatever I'm talking about, 2.4 or 1.8, whatever maybe, ISM, GSM, whatever maybe you can say that frequency should be interfered with whenever the close proximity with that sensor will be within a small region. So interference can give you some deterioration of the data. That's whatever.
Okay.
So could you check it if the two devices are very close to it, how they are interference with each other, or if you can using some other
Here also I can give them. First of all, you try. See, the same interference, whatever they said, it is happening. But the clustering techniques, main idea is to remove the interference only. We find out one interference, we find out that is the 245 degree temperature is coming, which is not
interference is a frequency domain. Interference not in time domain. The clustering is going to a time series data which is making as a different cluster. But how to overcome
that noise is removed from
Actually, our main task is to detect the noise, detect the outlier. Like
that's why I'm asking you in between whenever you are transmitting in that is where the edge computing is coming. So in the edge layer, whenever you are transmitting the data, there is a transform known as a Fourier transform. Do you know it? That frequency series data can be effectively transformed in the time domain. So that you can, if you do that thing, then the frequency interference can be interpreted by inverse Fourier transform in your data set, so that the frequency interference as well as the time series interference can be interpreted directly. That is called the OFDM technique, orthogonal frequency time division. That's how I'm coming out. Instead of taking the time series data, then if your scenario, particularly IoT scenario, we are talking about IoT scenario, it's an interference in frequency domain. That is a fundamental physics, not the computation of mathematics, mathematical or your computer science. It's a physical problem. So that's why the OFDM orthogonal computation is coming. So both cases you have to do this technique that is called the Fourier transform, and then the inverse Fourier transform, then make your data set. That will be orthogonal divisional techniques is there. That's just
so you can use these kind of things like in your
Yes.
Actually, there are many studies talking on the basically talking about from my point of view, electronics point of view, and this type of things, it is okay. But what is work? Our target is to introduce one algorithm which can deal with the real-time data. Real-time data means we are talking about those data coming streamlined from different sensors. Okay. And we have gone through different clustering algorithms like k-means and overall so many clustering algorithms are there. Then we have found that bars is the one who can deal with those type of machine data. But again, main problem with the bars is that it is somewhat sticky to the static data, not to the dynamic data. And we take that as a problem statement, and we have gone for the introduction of this RT parts, that is real-time partial algorithm. And there we have implemented two things. First thing is the parallel processing trading. Okay, and second thing, that the thresholding we are doing from adaptive way. Not just earlier they take some default values, but we are going from some adaptive thresholding, and that serves the purpose. Our main problem statement, that is being achieved for the introduction of this RT parts. And regarding the application part, he has shown that two applications we have already done. One for the student, that one, and another one is the resume classification. So this work is a blending of two things. One is the unsupervised, and that goes for the supervised. Unsupervised algorithm we use because real-time data, you cannot think of them as a level one. Right? We need to group them into some particular classifications, levels, and then push that to some classification algorithm. And we can see that the output is quite good. Right? Overall, the classification we have gone through is like 0.991 something. Right? So that is what actually serves the purpose. So whatever the suggestions our experts are suggesting is very good, really. But they are actually, I feel that somewhat diverting from our own objectives and problems. But yes, there is scope to work on that. A lot of scope, and I can say that interdisciplinary work is possible in this case. Electronics, computer science, and various other domains can work together for those problems.
So I will also considering for yes, like the agriculture is like you are talking about.
Yes.
Very high scope. Nice
Yes.
you are doing the topic. And very much like
Lots of challenges are there.
Yes,
First of all, who is going to give the power? It's a rural area. We tried with actually NVIDIA. That's the second one it is effective. So, but that is very good result. But you have to take the entire power infrastructure and that infrastructure.
then what happened in one then talk like Bora already from agriculture itself.
Yes, sir.
You can also identify.
Yes,
Because the collaborative work we can do.
He is core from the agricultural university. So
But again, we have to go to a rural area where the network and the power, nothing is there. Over there, we have to real time, we have to check it. Then this can be a real time industry application. Otherwise, it will be a problem. You are trying. But the thing that one domain is open. Earlier also we are trying, but we did not succeed. That real time data it is taking and giving the real time clustering with the massive data up to 1 lakh.
I have a question here. You said there are two areas where you did the improvement. One is the execution time, and the second one is with respect to memory.
Yes.
Execution time you drop from 580 to 523.
Yeah, that was in comparison with the existing state-of-the-art techniques.
Okay. So did you use any statistical analysis to figure out whatever drop was, whether it is statistically significant?
We did time complexity analysis, but apart from that, like we didn't do any.
Statistical analysis could have supported your data in a better way. Like how much drop is there, whether that drop is significant enough or not. Memory is quite evident. It is there is a huge drop. But 580 to 523, it is 57.
We are not getting down. It's a good idea.
So you can support your data with statistical analysis. You have also mentioned about burst data sets. Can you give some examples of burst data sets where it can find applications? You will
Yes.
in your future process.
Yeah. Burst data sets usually occurs. For example, we can take the classic example of Bora Rapido. So parallelly, we can just give a rough estimation at this particular time instance, at this particular second, how many Uber cabs are getting booked, how many Zomato orders getting placed. For us individuals, it is a single data point that we are serving or we are just supplying to the server. But for the main server, which Zomato has, actually everything happens nowadays is distributed platform. For them, it's a bursty data. Like bulk of data is getting populated to there, because every time a rider goes from one point to the another, for every milliseconds longitudinal data is being supplied. So with reference not only longitudinal data as well as the metadata of the rider, whether what is the bike number, what is the bike history is having, although those are static data, but the real-time data is the data time long with reference to the time. So if we compare throughout the globe, there are a lot of data points that are getting generated for both Uber, Rapido, or whatever these ride-sharing platforms are. So this can be an example. One more example could be, let's say, specifically in case of smart cities, where we have deployed sensors across all locations, across various locations, and all of them are generating this data. And ultimately, Saha has to handle. So within a second of time frame, if we see in our scenario itself, where we just had 6 sensors in 1 second time frame, we were getting 6 records. So in a 60 seconds of time frame, 360 records. So 360 records, that is for 60 seconds of time frame for 6 sensors. But if we multiply the number of sensors, and if we just see for 1 second, in that case, we will be getting 1 second of burst period.
So I'm basically looking your work from a healthcare perspective.
Yes.
So for example, during COVID time, there are a lot of positive cases coming out from particular location. They are uploading the data. So how the data is pooling now? I guess your this those data sets we can also find applications there. Which are the locations where you're getting more number of cases in a shorter period of time?
Yes.
For example, 24 hours is a huge spurt in infections.
Yes.
Or else you can find your applications in highways where number of vehicles entering a city. So those toll gate feed, you can get an idea. Okay, these many traffic has already entered, but they have not exited. So the vehicular traffic inside the city is going to be.
Yeah. Congested. That we have considered.
It's good work. You can find various applications.
Yes. Various applications.
Very good idea. Traffic identification, physical traffic identification, how much traffic can be.
It is the quality. Once you enter, you don't find the exit. Where good.
Okay. Thanks.
Thank you, Prabhat. From my side, this is a very good work. Wonderful. Thanks.
Any questions? Already
Mic mute.
Okay, ask all the-
Okay. What was mic mute? Sorry, mic mute.
No, mic is also.
No, I think
So I would like to thank first of all Ramas University and Professor Sajal sir, because the real implementation is done at the campus and that needs permissions, and sir help us, right? And
That's Adam's University funding also.
yes, funding also.
Without
Yes.
funding, it will not be possible.
Even that paper also, yeah, they help us.
Funding is done.
Yes. Thank you very much, sir. And thank you all the members here. And Anindita ma'am,
Yes, sir.
thank you very much, ma'am. So after all, we come to the conclusion, as I think no questions left to be asked. So I would like to hand it over to our controller. Pitam sir, are you there?
Hello. Yeah. Yes, sir. I'm very much there. Am I audible to everyone?
Yes, sir. You are audible.
Okay. A very good evening to all the esteemed panel members present today for the PhD Viva course of Prabhat Das. Well, the work has been presented in a very good way, good manner. I think our external expert, Dr. Anindita Kundu Madam, has already declared the result, but still I would like to take an official consent from ma'am that are we good to declare him for the award of PhD, ma'am?
Definitely, sir. Definitely.
Thank you so much, ma'am. And in fact, I'm extremely grateful to you for sparing your valuable time with us today and
My pleasure, sir.
and checking and all the hard work and the efforts that you have taken in examining the whole work in such a short span of time is really remarkable. And I really do hope so that in future also we will be able to collaborate for such academic works.
Sure, sir.
And maybe in the near future we would definitely like to have you amongst us in person for such works.
Sure, sir.
And
I'll try.
it was really pleasure connecting with you, ma'am. And I would request you that I have shared one form with you this morning.
Yes, sir. I
If
have
you could
received it.
kindly, yeah, if you could kindly fill it up and forward it to me, then
Sure,
we
I'll do
can
so. I'll do that, sir.
complete the rest of the formalities, ma'am.
Definitely, sir.
Uh, well, thank you very much, ma'am. And nothing much from my end to say, since person responsible for running the examination of this university, I am not supposed to speak anything about the work, whether in favor or whether in disfavor. But whatever the panel has decided, and especially whatever the external examiners have recommended, based on that, we will proceed. And thank you very much, ma'am, and all the esteemed panel
Most
members.
welcome, sir.
Thank you. Thank you. Thank you.
Thank you, Anamika.
Thank you, sir. Thank you, sir, for inviting me.
Now we can call Prabhat as Dr. Prabhat. All agree with that.
I would also thank Sajal University also for giving us this opportunity because he has started this work in 2020. So that time we are skeptical that if IoT type of work, if we start, it will get lots of funding and real-time implementation. Whether it would be possible or not. But Prabhat has shown this one, and both the universities have supported a lot. So such kind of work has seen the day of life. And thank you.
Thank you.
Thank you.
It's like 5 years, almost 6
6
years.
years. This was for 6 years.
And one way to say something, but actually, see, student,
BSc and
BSc
Integrated
and
NCI.
integrated NCI, that time I went to take this IoT class from there. How to go
So what is the only thing I did in Kazakh University who stayed long in Indonesia? From 2016 to 2014, 2014 to 2026. He was rejected.
computer.
Was
And those days he was in that class, he was doing that he will do something on IT.
Yes, sir.
That was the starting point of my
So would like to have a group photo. I mean, already there, right? So we can go there and I can have it. Please. This is your
John Cow.
Oh, yeah. এটা জিওটেক লাগি Thank you.
Thank you.
Well done. Finally done. Congratulations. Okay. So, some percentage you inform you. Thank you.
Five weekend.
Ma'am?
Yes, sir.
Fifth weekend.
Can give you. Yes, sir. Thank you.